Hello everyone, my name is Meron Goli, and I'm going to present a summary of my PhD thesis, Automated Design Understanding of SystemC-based Visual Prototype, Data Extraction, Analysis, and Visualization. Hardware complexity nowadays is a major issue. Modern electronic systems consist of many different functional blocks, such as multiple intellectual property cores, various on-chip interconnects, and memories. Currently, the Intel Xeon Platinum chip are manufactured as 8 multiprocessor systems on a single chip and reach up to 8 billion transistors. The classical hardware description languages such as Verilog and VHDL, which are widely used to model hardware at the register transfer level, cannot be easily used to run, test, or evaluate modern embedded systems at such low levels of abstractions. They increasingly face the issue of the design gap. The problem that a system cannot be designed in accordance with the available manufacturing capabilities due to its complexity. One possible solution to handle the complexity of the electronic systems and circuits is to raise the levels of abstractions toward the electronic system level, ESL. ESL paradigm has become an industry-accepted solution over the last decade and came with new design methodology, tool, and a specific system design language. Among the existing modeling languages, SystemC has become the de facto standard as it provides designers with a fast simulation speed. It covers all C++ features, event-driven simulation kernel, and strong support for hardware-software co-design. Moreover, one major advantage of SystemC is its TLM framework, which provides designers with even faster simulation speed and more abstract model. Designers use SystemC and its TLM framework to model a system as a virtual prototype, which is basically an executable software model. In comparison to RTL, VPs have significantly faster simulation speed and are much earlier available. This leads designers to use VP for architectural exploration, performance analysis, early software development, and overall reference model for lower levels of abstraction. To create this reference model, designers need to perform several steps such as debugging, verification, security validation, and design space exploration. However, performing the aforementioned tasks requires detailed knowledge about VP's structure and behavior. The question here is, what is the possible solution to access this information? A straightforward solution is using some ad hoc methods such as reverse engineering by reading the documentation or manually altering some parts of the source code to extract runtime data. However, the result of this analysis is incomplete, error-prone, and requires lots of manual effort by designers, especially when the VP includes some third-party IPs for which no documentation may be available. On the other hand, using a strong design understanding tool can provide designers with detailed information about the VP's structure and behavior in an automated, comprehensive, and accurate fashion. Therefore, using design understanding tool is essential. Existing VP design understanding method come with several drawbacks such as manipulating a standard SystemC workflow like library, interface, or SystemC kernel, limiting language construct, low degree of automations, lack of extracting detailed runtime behavior of the VP, and finally, lack of supporting TLM construct. To overcome the drawbacks of the existing methods, our proposed approach is based on two main phases, which are information extraction and data analysis and visualization. In the first phase, we take advantage of debugger and compiler as two infrastructure for information extraction. In the second phase, we perform a post-execution analysis to translate the unordered extracted data into a set of classified intermediate representation. Moreover, we visualize this classified information in such a way that designer can quickly grasp the intricacy of VPs. In the debugger-based approach, we take advantage of the GNU debugger (GDB) as the underlying infrastructure. To describe the VP's structure, the static information of the VP is extracted by analyzing its debug symbols, which are directly generated from its executable binary model. To extract VP's behavior, a smart combination of the extracted static data and basic feature of GDB is used to automatically program GDB for runtime data extraction. In the compiler-based approach, we take advantage of the Clang compiler as the underlying infrastructure. To describe the VP structure, the static information of the VP is extracted by analyzing the abstract syntax tree AST of the VP's source code. To access the VP's behavior, an instrumented version of the VP is automatically generated from its AST, including the instructions to retrieve the runtime data. The generated runtime log file from the previous phase contained unordered information about the VP's behavior. Therefore, a post-execution analysis is performed on the extracted runtime data to generate a set of intermediate representation of the VP's behavior. Moreover, to help designers in understanding the VP's complexity, these IR models are translated into a set of UML diagrams for TLM VPs and VCD file for cycle-accurate model of VPs. Here we can see a part of our experimental results where our proposed methodology are applied to the real-world Leon tree-based Sockrocket VP. The VP includes more than 50,000 lines of code distributed over more than 100 files. Our design understanding tool was able to extract 1,000 transactions, and the result of its data classification showed that the VP includes 19 unique communication flow where IP cores communicate each other with 8 different types of transactions. To show the VP's unique behavior, our tool generates 21 UML diagrams and 1 XML model to show the VP's structure. However, none of the existing approaches can provide designers with the same analysis and results. While the execution time of our analysis lies in the order of minutes, to obtain similar results using the reverse engineering method for such complex VP may take days. This slide shows a summary of our proposed design understanding methodology, including 2 main phases, which are information extraction and data analysis and visualization. In the first phase, we proposed 2 novel data extraction approaches, which are based on debugger and compiler. The common advantages of our data extraction techniques over the existing methods are they do not restrict or limit the language constructs, they are fully automated, they support both cycle-accurate and TLM VPs, and they provide designers with detailed information about the VP's structure and behavior. Furthermore, each of the proposed approaches has its own advantages. The debugger-based approach is fully non-intrusive and can even work when no source code is available. Therefore, in the case of third-party IPs where the source code may not be available at all, it is the only solution. The compiler-based approach is very fast and scalable with an arbitrary complexity of VPs. In the second phase, we enhance the understanding process of the extracted data by generating a set of IR models, by classifying the extracted information, and finally, by visualizing the VP's behavior in terms of UML diagram and VCD file. In the last part of my talk, as an example, I would like to show how our design understanding methodology could enhance the VP verification at the ESL. When we say that VP is a reference model for lower levels of abstraction, verification of the VP is of utmost importance, as the undetected fault may propagate to lower levels of abstraction and become very costly to be fixed. However, the existing VP verification methods come with 2 main drawbacks, where formal methods have a scalability issue and simulation-based methods require lots of manual effort by designers. Our proposed verification approach consists of 4 main phases. In the first phase, we take advantage of our information extraction techniques to extract the runtime behavior of VPs in terms of transactions. In the second phase, the runtime behavior of VP is formally presented as a set of time automata model. In the third phase, the VP specification and TLM protocols are translated into a set of properties. And finally, the behavior of VP is verified against the generated properties using UPAL model checker. In summary, we have proposed a design understanding methodology from 2 perspectives, which significantly enhance the VP analysis at the ESL. With the help of our design understanding tools, designers can perform various tasks in the design process faster, more accurate, and errorless. The comprehensiveness and automation are the main advantages of our proposed approaches. We published our proposed techniques and the result in outstanding journals and conferences such as TCAD and Today's journals and ICCD and DATE conferences. Thank you for your attention and have a nice day.